Okay, so we are going to go through example 7.2 of chapter 7, the second example of the book. This is in this example we want to find the V0 at the ends of this over here. We want to find the V0 when the switch is on. So after t equals 0, so before t equals 0, this circuit was connected, and then as soon as we open it, we want to see the change in the current that is causing a voltage over here. How is that going to change the voltage that is appearing at these two ends? Okay, before we start, before we start to solve the problem, we need to know at time equals 0 what was the current flowing in this part. And we all know that when it is when we are in a steady state, a solenoid or a coil is considered to be short circuit. Okay, in order to find this current, I'm going to look at it like from Thevenin point of view, and I'm going to take this part out. I'm going to take this part out and then look at how much is the voltage that is appearing over here and how much is the current that is flowing into it. In order to find the current, first I find out the voltage that is appearing at the ends of it. As you see over here, I have redrawn this circuit, and I said that okay, if I have a 2 ohm over here and a 2 ohm over here, and I'm looking at the voltage across this, so what is the voltage that is appearing, the open circuit voltage that is appearing over here? If I want to find the open circuit voltage, it is very easy. So basically there's a 12 volts over here, there's a 4 volts over here, and then 2 ohms, and then I just need to find the V at this position. In order to find the V at this position, I am going to first find the current that is flowing in it. In order to find the current, I say that okay, I have a 2 ohm over here and a 2 ohm over here and a 4 volt and a 12 volt. So starting from here, so I have so the total amount of voltage that is available is 4 volts, 12 volts plus 4 volts, which is 16 volts, and then the total resistance is 2 plus 2 ohm. It is going to be 4 amperes. So 4 amperes is actually flowing from here, is 4 amperes is flowing into this, in this side of the branch. Okay, so how much is the voltage over here? So if you start from voltage, so from here to here I have 12 volts, and then 12 volts minus whatever voltage is dropping, 2 times 4 amperes, so 12 volts. So V of open circuit, V at this point, from this point, is the 12 volts minus 2 times 4, which is the voltage drop at this resistor. So I'm going to have the 4 volts. So this is 2 times 4 is 8. 12 minus 8 is 4 volts. So the V open circuit is going to be 4 volts in our case. The second thing I want to find out for the R Thevenin, for the Thevenin equivalent, is what is the R Thevenin. If I want to find the R Thevenin, I have to short this one and short that one, and then see how much is the resistance over there. So if I short these two, I would see that, so R1 and R, so this is shorted, so R1 and R2 are going to be in parallel. So 2 equal to 2 is going to be 1. So we all remember that when two of the resistors have the same values, then your resistance is going to be half of that. So if I look at my circuit, then this circuit, what we did, we opened it from here, and then we want to replace this part with a Thevenin equivalent. If I put the Thevenin equivalent of that there, then my circuit is going to be a 4 volts, as we found the voltage over here, 4 volts, and the current that is going to flow through it is going to be 4 amperes. Is the current, we are not talking about the current. We have 4 volts, and then the resistance is 1 ohm. So there's a 4 volt and then 1 ohm connected to it, and then it is connected to our L, and then it is connected to our R, which is the R3 equal to 2 ohm. But okay, so what do we want to find now? We want to find the IL. How much is the IL before we start? So that is the important thing for us. In order to find the IL, I'm going to find so this is exactly like I have to take this into account as a short circuit, because we said that in steady state this is just like a short circuit. So the IL is going to be my voltage V over R. So my voltage is 4 volts and R is 2 plus 1, so it is 4 volts plus 2 over 2 plus 1, so this is 4/3 of ampere. So this is the current that is flowing at IL when we are before opening that. So before opening that, so as you again one more time I say that we took into account the Thevenin equivalent. So we found the Thevenin equivalent to be in 1 ohm and a 4 volt connected to this, and then we found the current that is flowing in it is going to be 4/3 of ampere. Okay, in order to find out what is going to happen when this is open, then I open it and then look at it. So if I open it, this is my case. If I open my switch, so when I open my switch, this part of the circuit is going to go out. So basically I'm going to have a 12 volts over here, R1 2 ohm, and the 2 Henry solenoid, and the 2 ohm resistance over here. So if I write the KVL over here, then I have starting from here, if I start from here, so minus 12 volts, so is minus 12 volts plus R1 I1. R1 is 2 ohm and times I, so 2 times I of t, and then plus, then the I over here is going to change, so the V is actually I L di over dt plus so there is another voltage drop over here, so I have 2 ohm times the I, right? So it is 2 times I of t equals 0. So this is my KVL. So this KVL, this is my KVL, and if I want to find out the answer to this, I have to simplify it. If I want to simplify it, so this 2IT and 2IT is going to give me 4IT, and then so there's a 12 over here, and the L was also 2 Henry. So I just put a 2 Henry over here. So if I divide everything by 2, so this is going to be 6, this is going to be 1 and 1. Okay, so there's going to be 2T over here. So my answer, my simplified equation is going to be di over dt plus 2I of t, and this is also I of t, equals 6. So this is my simplified answer. So now we have to go back to see what was our answers when we were looking at an equation like this. So we said that if I have dx over dt and plus x, so these are all these are all with a function of t, equals to ax equals to capital A, then my answer is going to be what? My answer is going to be x is going to be k1 plus k2 e to the power minus at. And then I said that k1 is actually capital A over small a. So k1 is capital A over small a, and in order to find k2 we have to find the solution at time 0, then we find k2. So we do not directly put k2 over there. So let's find the answer to our equation. So di over dt is So I say the over to, so if I want to find out, so my I is going to be K1, which is A over A, capital A over here is 6, small a is 2, so this is 3. So A over A for us is 6 over 2 is equal to 3. So 3A, so this is 3, and then plus K2 e to the power minus AT, minus our A is over here is 2, minus 2 times T. So this is the overall answer, but we have not found K2 yet. So in order to find K2, I have to put this at time 0. So I at time 0, t equals 0, is equal to 3 plus K2 e to the power minus 2t at time 0, at t0. So 2 at time 0 is going to be 0, e to the power 0 is 1. So my answer is going to be, what is my I at time 0? My I at time 0, we found it over here. I at time 0 was 4/3 of ampere. So 4 over 3 equals 3 plus K2. Then our K2 is going to be K2 is going to be minus 5 over 3. So this is going to be 4 over 3 minus 3. This is going to be minus 5 over 3 if I solve it like that. So my answer is going to be I. So I'm looking at here, I equals 3 plus K2, because I now know what K2 is. So I write it as I is equal to 3 plus, minus 5 over 3 e to the power minus 2t. So this is my answer. And then we would see that our equation is going to, the relationship is going to look like an exponential decay, and the only difference is that in this decay we are going to start from so this is it is not going to be decay, so it is going to actually increase, because this is the amount that is decreasing. So 3 plus 5/3 of e to the power minus 2t. Okay, so I hope you can also do it once yourself and then find the answer as we did in this problem over here. But only one note that I didn't say was that this A is again the A that we have over here in our relationship. The A that we say A is the same as what we had before in the previous problem about the relaxation time. The relaxation time in an inductive circuit is so tau is again 1 over A, just like what we had before, and then this time it is not RC, it is actually R over L. So this is just something I wanted to bring it to your attention, that A is 1 over relaxation time, or relaxation time is 1 over A, and in our case is R over L, and that is what actually we have used over here for the A, and this is minus 2. Okay, thank you so much.